All right, so we'll just continue from where we left last time. So I tried to cover mostly the MOS transistor large signal model and just introduce the concept of small signal, which was the incremental analysis. So what I'm going to do is next maybe 5-10 minutes, I'll just quickly recap whatever we did, and then I'll continue with the rest of the material. All right, I think the first thing we started was with MOS transistor operation. So I'm going to just show the two-terminal device use of the MOS transistor. And we're following this notation here. And like as I said, again to repeat, the source and drain are really symmetric. It's how you bias it. So once I show it as a source, that means it's a lower potential than the drain for NMOS, and for PMOS it's the opposite. And usually the bulk is shown as another terminal here. So we showed that if we connect all this terminal together and let's say we bias it with some, I'm going to call this VGS, although the source node is all three nodes connected together. And then if I draw the capacitance of, so this is the voltage VGS, and this is, let's say, the capacitance across those terminal. So let's say C. Then we said that there is no channel formed. So as we keep increasing this voltage, we start with 0. There is no channel formed. That means there is this channel is not inverted yet. So it's just a depletion mode, which means that there will be no charge formed there. So if I look at the capacitance, it kind of looks at 0 till we reach the threshold voltage, which is called VTN for NMOS. And then the charge starts getting formed. So the capacitance just looks, so if you look at this capacitance density, for example, it just looks like the oxide capacitance density, right? Oops. And then if we go negative voltage, we saw that we get into a region called the accumulation region. And it's not exactly COX, there's a depletion cap too, but we'll assume for now that that's COX as well. So we kind of get this region of no charge. So there is no charge here. And then as you go above VTN, you get COX. So we actually use this as a capacitor. Like as I said, in IC design, you don't have the luxury of a lot of passive devices you get, like for example, when you do board design. So a lot of times you have to use these devices as capacitors, and usually they are high dense. They are the highest density capacitors in a IC design. So wherever you can. So you can see that you can only use this capacitor if you have a DC voltages greater across it. So let's say you have some bias voltage and you're applying some small signal here, and you want to look at it as a capacitor, then you can, as long as this voltage is greater than VTN, right? Sufficiently larger. Usually you want it to be 100 to 150 millivolts larger than that. So that's how the two-terminal device looks like. And then we said, okay, now once the terminal is formed, how do we make the current flow through the drain? Because that's really what mostly the transistor is designed for, because capacitor, you can just put two plates and you'll get a capacitor. You don't have to do a fancy device for this. So the main use of this device is actually to use it as a switch or a gain device. So then we said, okay, we bias the gate to source voltage, and we'll call this some VGS, let's say 0. And then we apply a drain to source voltage, and that's VDS, we call it VDS. And then we try to find out this current which is flowing through from the drain to source as a function of VDS, as a function of VGS, and also the source to bulk voltage. And I said that this bulk voltage has to be always, so if you write it as VSB, it has to be less than 0. I'm sorry, the other way around. So if you want from source to bulk, that this voltage here, yeah, I think I had it right, greater than 0. A lot of times we write bulk to source voltage, which needs to be 0, less than 0, negative voltage. So essentially you want this bulk to be at the most negative voltage compared to the rest of the nodes, because like as I had shown last time, you actually have a diode form like that. And for PMOS, it'll be exactly the opposite, right? So that's your bulk. Let's say this is your source and that's your drain. So you have these two resistors, two parasitic diodes, which you don't want to short them. So that's why this bulk voltage always needs to be at a negative voltage compared to source, or a negative voltage compared to the drain, right? Now, if we draw the transfer characteristics of this device now, we showed that if we plot the IDS, for example, versus VDS for a given VGS, and we assume that the VGS is greater than VT, which is called the active region, then this transfer function is going to look something like that, right? So we get this really small region here for really small VDS, where this looks like a linear resistor. So the IDS will be equal to the mobility times the oxide times the scale factor, which is W times L. So the larger the L, the higher current, the higher the L, the less the current, right? And VGS minus VT, and in this case times VDS. And this term we always call it as V effective, or sometimes call it V on, or sometimes call it V overdrive. So all these terms here, they mean the overdrive. So basically means how much of the gate source voltage is higher than your threshold voltage, okay? And this is a linear region. So actually this term here is nothing but looks like 1 over R, right? And as you change your VGS, so this is some VGS 0, let's say this is VGS 1, which is less than VGS 0, and so on. So for different voltages, you get that. Now for this region here, we said the IDS looks like mu n Cox W over L VGS minus VT whole square. That is an approximation, but in reality, this, because of the channel length modulation, you get an increase, and that's why you get another 1 plus, I'm sorry, this is, you get a channel length modulation term, which is 1 plus lambda times VDS minus V effective, right? Sorry, it's not clear, but I think you can refer to the other nodes. And I think somebody asked me last time that how is this linear when this term is nonlinear? So yes, if you draw the resistance versus VGS or V effective, let's say, then yeah, this is a nonlinear term. But at every point here, like you choose certain V effective, these points here are actually these lines here. So they're linear as long as you have VDS equals to 0. So I'll show a problem towards the end. I think pretty much everyone missed that problem, the 1.22, which shows the bandwidth. That's actually perfectly in a linear region because the VDS is almost 0. So you'll actually use this equation. And here, this region here, you have a nonlinear equation. I won't write it for the sake of time, but we usually never bias our devices in that area. Most of the time, we're actually biasing the device in this area because that's where we get the highest gain. and subthreshold region, which, when we get to the projects, we'll talk more about it. So when we get to low power designs, we'll talk more about it. Okay, so that's a quick recap of the large signal model. And then I talked about a small signal model, and I gave a big long sort of motivation on incremental analysis, why we do small signal. And like as I said in the lecture, it's trying to linearize a nonlinear curve, right? So like, for example, this is a diode curve, it's a nonlinear, and it's harder for us to do analysis using nonlinear equation. And we said that if you know that your signal is a small signal around a certain point, then you can actually linearize the curve. And we showed that with writing the Taylor series expansion and showing why it's the slope there, as long as the voltage or the current, whatever it is you're applying, is small enough. For example, this is small enough, because as this goes higher and higher, you can see this error term starts increasing, right? Maybe later on I'll show you with more analytically how, as your voltage increases, how the error term also increases. Okay. And then we said, the 3 steps really to the incremental method is you actually start with the operating bias point, because since it's nonlinear, the device characteristics changes with different bias points. So you want to fix a bias point, otherwise you won't be able to do this. So you fix a bias point. For example, if you're doing a diode, you fix the voltage across it, which will fix the ID across it. Now you superimpose a small signal across it, and then so that'll be the small signal part of it, and then you find out the response to it, which is approximately linear, by linearizing it, right? So that was the crux of incremental analysis or the small signal analysis. So every time you're taking a slope of something and trying to find small signal, always remember it's about a bias point. That's very critical. Okay, so that's a quick recap of what we did. So I'm going to start with the rest of the material, and I think I'm just going to jump straight into the small signal of the MOS transistor. So the first thing we're going to talk about is the transconductance, and that's probably one of the most important parameters of the transistor is this transconductance. And the transconductance is essentially, so if you take a NMOS transistor, for example, so we said, we take NMOS, and we said for it to be in the active region, we bias, like before, a certain VGS, which is greater than VT, and we apply a VDS. And typically in these cases, the source voltage is connected to the ground, but may not be so, right? So that your source to bulk voltages. Now, we saw that the current equation ID, right? Current equation ID is mu n COX. This is in the active region, is VGS minus VTN, which is the V effective voltage. That's the equation, right? So you can see that this is a nonlinear equation, right? So if I draw, for example, the IV characteristics of this, so that's your IDS, and that's your VGS, and then for the voltage till VTN, it is 0. Well, almost 0, because we can actually operate it in this region called the subthreshold region, and where the gain is actually the highest, but the current densities are low. So that's your nonlinear equation. So let's say we want to operate this at certain VGS, and we give a small signal, let's say VI, right? And we want to find out what the small signal delta I is. Or for example, in a lot of your problems, I think you've been dealing with self-gain. So essentially self-gain is nothing but, so let's say we take this transistor here and we bias it with certain current source, let's say some IB here. and we give a small voltage across it, and we give some DC bias VGS, and we want to find out. So let's say this is small signal VI, and we want to find out V naught. So the self gain, which we call it AI, is nothing but V naught over VI. And we've been writing this as GM times RDS. I'll show you why that's the case. So the first thing we want to find out is what is the response of delta I, which is flowing into this. So what is delta I compared to delta V, which is applied to the gate. And because this equation is nonlinear here, like we said before, I need to find out in order to make a linear approximation or a linear analysis, I need to find out what the bias point is. So for example, in this case, I apply a bias voltage, a bias current IB. So let's say this is IB. So that'll be my operating point. So that'll be some equivalent VGS 0 here. So I need to linearize here, right? Linearize around this point, and that is nothing but your DIDS versus DVGS, and that term we call the transconductance or GM. That's small signal model, right? And I won't go into the details of the equation, but as you saw in your material, there are, let me just bring up a new slide here. So we saw different expressions for it, and I'll write 3 main expressions for it. So I think the first one you saw was, GM is equal to mu n COx W over L V effective. And then the second expression was GM is root of 2 mu n COx W over L times ID. And then the third expression, which is probably the one which is most important when you're starting to design, is 2ID over V effective. So the question is, what expression do I use? Well, it depends. All of them are obviously the same expression. It's just algebraically you substitute V effective or ID in places and you get all these expressions. So like the first one, you can see that this expression is not dependent on ID. So if you know your W over L's, and this is always a constant, so obviously that's given to you. That's a technology parameter. You know your W over L, and you want to find out how GM changes with V effective, you use this, right? And the second one is the other way around, where if you know your sizes already and you want to see how it changes with ID, you use this equation and you can see it's a square root of ID. But this is probably one of the most important, at least I find it most useful expression while you're designing it, because the reason it is useful is like in your design, mostly when you start doing analog design, you'll see that in your project, usually a current is given to you. You never design with voltage sources. Your biases are always through currents. And the reason for that is because if you do it with voltages, your currents will change dramatically over process temperature and so on. So what you do is you generate fixed currents, and we'll actually create a project to generate a band gap and current, which is one of the key elements in pretty much any analog chip. So you're given an ID. So if you're given an ID, and this V effective is nothing but what's called your headroom. So for example, that simple source follower example I showed, or you guys haven't done source follower yet. I think it's there in that same section I forwarded to you in this assignment. But essentially it's this configuration, right? So you give certain VI and you want to find out what's your V out. And that's really what transistors are used for. So in an IC, you usually always bias it with a current source. You never bias it with a voltage source. And this voltage is what is generated because of this IB. And we'll see different ways to generate that. So, and this is really a useful equation here is because let's say I tell you like, okay, maximize this gain, right? So you say, okay, I need to find GM times RDS. which is actually 2 times, I think, lambda V effective. And typically in a IC design, in any project, you'll be given a certain supply. So for example, this will be VDD, which can be your battery voltage. Let's say, for example, this is just 3 volt, which means that you're restricted how much this voltage can swing here. So you'll be given certain headroom, right? You'll be given some V headroom, which is, let's say I call it some VHR. Now that tells you that you cannot, your V effective cannot be greater than this. So your V effective of that transistor needs to be always less than V headroom. So you're given a current, you're given this headroom, that means you know what GM you can get out of it. So if you need more GM, that means you need to pump in more ID, and you have to change this W over L to keep the V effective to maximize this or minimize this depending on what you need. And as we do more examples, if you're not exactly following, it's fine. As we do, I just want to give you a feel of like why one equation is important to you than the other one, right? So in most designs, like as I said, we'll be using this equation, but that's not necessarily true. For example, like as I said, if your device sizes are fixed and I tell you to find the current for a given GM, then you'll use this equation. Okay. So similarly, there is a small signal parameter called GS, which is the body effect parameter. Okay. So for example, if I give you the same transistor and your VGS is fixed, your VDS is fixed, right? But your source voltage is actually changing. So you have some certain VSB here, and you have a small signal here for some reason. Then that current, because if you write the current equation, for example, if you write the current equation in active mode again, so most of the time we'll be talking about active mode, then this is VGS minus VT square, right? But this VT is actually a function of VSB, right? So which means that if this VT is increasing, this current will decrease, right? So if VT is increasing, ID will decrease. And VT increases with VSB increasing, right? And that's the equation I showed you last time. I won't rewrite it, but just take it for granted. So the small signal factor, sometime in this book, it's called GS, but a lot of times it's also called GMB. So you'll find in literature GMB that they mean the same thing. So that small signal is actually your DID over DVSB for a given VSB equals to some VSB 0, right? By the way, I didn't write explicitly, but the previous equation also, when you're finding this differential, you fix your DC voltage. That goes without saying. So that's your what's called the body effect or the body effect small signal parameter GS or GMB. And a lot of times, actually, your bulk and source are shorted, so this term is usually 0, but not always, and sometimes it's a very small factor. So when you're doing hand calculation, usually you just neglect this. You don't, unless this is a critical factor for you, right? Okay, so the last low frequency small signal parameter for the MOS is the output impedance. So that's basically if I draw the drain current versus VDS, we draw this curve. So I'm just exaggerating it. But the output impedance is really this slope here. So usually it's called R0 or RDS in this case, and that's DIDS versus DVDS. And again, it's for a given VDS equals to VDS 0, some voltage. But you can actually see that, I drew it linear. It's not exactly linear, but if you find R0 for any of these regions, they're actually pretty close. So that's why you probably notice that, when we write the RDS equation, oh, I forgot to give you the expression for GS. And just for completion's sake, like as I said, sorry. Again, for most hand calculation, you won't be using this, but I'll just write it for a completion's sake. So GS, that small signal factor is ga gamma, which is a body effect parameter, times GM, actually, which is your transconductance factor, times VSB, which is your DC voltage at which you are biasing the source to bulk, times 2 times phi, which is your work function. Again, this is just so that you know, but for hand calculation, mostly you won't be using this. We'll use the simulator. And again, I won't go to the detailed derivation, but you can see that this ID was equal to some ID sat, and this ID sat is nothing but mu n COX times W over L V effective square. That's what I call ID sat. So that's the current at this point right here. So I call this as ID sat, right? Times we had that 1 plus lambda times VDS minus V effective, right? So if you take the derivative of this equation here with respect to VDS, this is nothing but, sorry, this RDS, which is derivative of IDS over VDS, that's nothing but, actually, this is 1 over RDS, sorry. So a lot of times we call it the conductance of drain to. So GDS is equal to 1 over RDS. A lot of times we call this G naught too, the output conductance. So RDS is 1 over this, which is 1 over lambda of ID sat. Now, you've probably seen in your problems, you've approximated this to, if you know a drain current, you just write ID. And the reason for that is, you can, although I've exaggerated, in reality, the change is very small. So if you know ID sat or ID, they're pretty close. So if you substitute this, the error in your output impedance is pretty small, right? So you can use, so if you know a drain current at certain point, anywhere in that curve, you can use that to approximate it. So for hand calculation, that's good enough. Okay. All right, so let's construct the low frequency small signal model. The reason I say low frequency is that, so in IC, you have resistors and capacitors and transconductors, the 3-terminal devices. There are no inductors. And the reason for that is the value of the inductors for any wires are so small that we never care about it. Like, for example, if you take a small metal line of 100 micron, they're usually about sub-picohenries. So sub-picohenries in these kind of feature sizes and all that, they're pretty much um, uh, inconsequential. So that's why we never talk about inductors inside, unless you want to build inductors. So there are ways to build inductors, but otherwise not. So your biggest parasitic component is your capacitor, right? So when I say low frequency, what I mean is that at DC, and at DC, you know that a capacitor is open, right? So we are not considering any of the parasitic capacitance here. So that's why it's called low frequency. And we'll get to the high frequency small signal model, but we'll skip it for now. When we get into frequency response of small signal amplifiers, which will probably be the next week or the week after that, then we'll come back and do the entire small signal model where we'll put all the parasitic capacitors too, right? So if I construct the small signal model now, so maybe I'll also, take this moment to say how you're all probably familiar, but I'll just repeat it. So, for example, we took that common source amplifier, right? And we had some gate to source voltage and some overlapping small signal voltage VI here, VGS, and then a current source IB, which resulted in some VDS. So that's your drain node, that's your gate node, that's your source, and you also have a bulk, which, let's say for now we have some, sorry, it's the negative bias. negative bias here. So that's your VSB, right? Okay, so if I want to construct the small signal model for this, and the reason I want to do small signal is, let's say I want to find the gain, right? So let's say that's your small signal output, and I want to find out, and you've been writing the self gain in problems here, which is nothing but this V naught over VI when you bias it in this fashion. Because here it's called self gain because the output impedance of this element here is infinite, right? So we're just taking a ideal current source. The R naught for this is infinite. So that's why it's self gain, because it's the GM time of this times the RDS, and we'll see how that comes into picture. So when you do that, you basically take all your independent sources and make it zero, right? So you make your independent sources equal to zero, which means current sources are open and voltage sources are short. Okay? So if you do that in this, the VGS will be a short, right? And IB, this is the ideal current source, so this will be a open. And you draw the entire small signal after that. So we have only 3 nodes after that. So 3 nodes are gate, drain, and source. So I'll draw the gate here. So that's your, let's call that gate node. And I'll draw the drain node here. So that's your gate, that's your drain. And I'll draw this as source. And I'll make this my common node. And the only reason I do the common node is because it is common in this circuit. But it is a, what do you call it? Sort of a multipolar system. In other words, you can make the drain as common node, gate as common node, source as common node, doesn't matter, as long as you have all the elements from each of the terminals, okay? So the small signal voltage VI here appears across gate to source. So I apply that VI, gate to source, and that's your small signal VGS as well. And then from drain to source, the first element we're going to write is GMB, right? So that's your voltage controlled current source. That's your GM. Now, one important thing in small signal is this is a voltage controlled current source. Now, which direction do I have the current in? Because it's not a DC voltage, right? So for example, when you have a DC voltage and you give a resistor, for example, and this a V, you know the current is going to flow in this. But this current actually is not a flow of electrons. It's actually a phase relation, because we're talking about small signal. So usually it's a relation or an incremental voltage change. So if you have an incremental voltage change here, delta VI, the question is the delta ID, which flows here, which direction does it flow here? Now, if you increase the voltage in this direction, the current from IDS will increase, which means that the phase should be in this direction, right? So that's what direction means. And it could be very confusing in the beginning, like trying to figure out what a current source in a small signal means, but it just means incremental change in voltages to incremental change in currents. So if your incremental voltage is changing in a certain direction or a certain phase, and if it is exactly the same phase in the incremental change in current, you keep the direction in the same. So what happens is when you start writing the current times resistor and all that, everything sort of becomes coherent. Otherwise, you'll get your phases wrong, right? So you have to be careful with that. So now the question is, we have a drain, another small signal model, GS, which is source to drain current, but the voltage is actually source to bulk, which is multiplied to this. So so this is I should write the whole expression. This is GM times VI, and this is GS times VSB, okay? So now the question is, which direction should this current be in? Now, as you saw in the last slide, as you increase the source to bulk voltage, the current in the drain actually decreased. So if this is your direction for the same phase of current, this should be in the opposite phase, because that will make sure that the current which is flowing out or in of this is subtracted from here, right? So that's the direction you should have if this is your VSB, or source to bulk voltage in positive relation. And the last small signal parameter which you should have in this model is your output impedance, which is from drain to source, which is RDS. A lot of times we just write R0, right? So that's your complete low frequency small signal model for a MOS transistor. Now, like as I said, most of the time this bulk to source is shorted, where means is VSB equals to 0, which means that this term is also a 0, right? So all you get is this GM and RDS term. And you can see from here, that's what the self gain means, because if so that's your V out. So if I want to find out the relation between V out to VI, I won't go through the entire equation because it's pretty easy to figure out, because all this current which is flowing out, which is GM times VI, is actually flowing out of this RDS, which means that V out is equals to this current flowing out times RDS. So that's nothing but minus GM times RDS, right? And that's why we call it the self gain, because if you don't have any other load on that transistor, if you bias it in the active region and you put a small signal at the gate, the output voltage will change with this factor. And that's really what we use the transistors for, because it actually gives you a power gain, actually. You can't get this term just with passive transistor. All right. Is it pretty clear so far, or do you have any questions you want me to maybe what I'll do is I'll take one of the problems. I won't go through all the problems. I think maybe we have like 10, 15 minutes more. So I'll just go through one of the problems. Is it okay, or do you have any questions? All right, let me go ahead with the problem. So I think I'm going to choose this problem 1.20. So basically what was asked here was, so this design was for a 0.35 micrometer NMOS design. So I think it was asked, so yeah, so it's biased. So it's an NMOS, and it was said that it's asked that it's biased at a ID of 0.35 milliamps or 300 350 microamps. So obviously, for that to flow, you need to bias this at a certain VGS. And obviously you have this is a small signal. So you're gonna apply some small signal here. And it's basically as they want a self gain. So like as I explained before, so they want this V naught over VI, which is the self gain, equals to 35. So in this problem, they want to find out what your W over L is, right? Okay, so so since it's required that a certain gain needs to be achieved, so the first thing you do is you write the expression for the self gain, which we showed from the last small signal, that it's small GM times RDS. And so here again, if you want to write like for example, if you ask me, okay, which one do I choose? Which GM equation do I choose? Little bit of is from experience. So from experience, you'll know that, okay, I just want to find out expression which, because I know ID and I need to find out V effective, so I'll use this equation. And RDS is obviously always 1 over lambda. And I won't use ID sat here. Like as I said, I can approximate with ID here just to make it simpler. So ID cancels, and basically it's 2 over lambda V effective, right? And this should be equal to 35. Now, one thing I should have emphasized is that RDS, you know, this term here, so maybe I should just emphasize here, RDS is equal to 1 over lambda ID, right? So if you want a higher RDS, you can either decrease your lambda or decrease your ID. But in this case, your ID is given, so you're fixed with that. And you've probably seen in the table 1.5, lambda times L is a constant, right? Which means that this lambda is inversely proportional to 1 over L. So if your ID is given and you have to choose a certain RDS, that means the only other option is L. So you have to find out what that L is for this given effective transistor. Now, obviously, you have two unknowns. You can choose just a particular L and then find the effective V effective for that. So the first thing I would do is just choose minimum L, because that gives you highest gain, smaller CGS and everything. So I would just start with L equals to 0.35 micron mirror, and then use that lambda times L. I think for this technology, it's given 0.16, which means that lambda is 0.16 over 0.35 micrometer volt inverse. I'm just omitting all the units, but just pardon me for that. I just don't want to waste so much time. So if you substitute that over here, you'll get V effective is equal to 2 over lambda, which is 0.16 over, so this is lambda times 35 here. And if you substitute all that, you'll get 0.125 volts or 125 millivolts, right? So essentially what it means is that if you are asked to bias it at a current ID of 350 microamps, you have to have this VGS excess voltage of 125 millivolts. So VT for this device, I forget, I think it's 0.57. So you have to apply a VGS, which is 125 millivolts above that. That will make sure that the current flowing through this is 350 microamps, and that'll also make sure your RDS is 1 over lambda ID sat, which is equal to GM times of that should be equal to 35, right? So essentially it's a bunch of algebra, but try to get an intuition. So basically when you're asked to give an ID, if you're given to find W over L, the way you find the W over L is like, what's the V effective? And this is a little bit messy here because I'm trying to get everything done, but we'll post you the solutions. I think from that it'll be a little bit more cleaner and you can go through it by yourself if something doesn't make sense here. Okay. So I think maybe next one, I just want to quickly go through that last problem, which I think pretty much nobody attempted. And I just want to make sure everyone followed that. I think it was the problem 1.22. So basically you're given NMOS transistor, and this was your VI, and you had a capacitor, I think for 1 picofarad here, and that's your V out. So basically what was asked is, I think this was biased to 1.8 volts, and it was asked, this is at a DC of 0.3 volts. Now, you can just clearly see that because this VGS is much greater than VTN, this is always on, and there is no current flowing through this because this is a capacitor. So at DC, basically there will be no current flowing through it. So this will be 0.3 volt also, which means that the VDS is basically almost always at 0 volt when it is at a steady state bias. Now, obviously, it wasn't clear. I think a lot of you or few of you who applied this, try to solve this, you use a nonlinear equation, but you don't have to, because I think it's assumed in this, when a certain question is asked like this, where you are supposed to find bandwidth, it's assumed that this signal is pretty small. Okay, so which means that once you bias it, even if you put a small signal over here, where that means that this VDS is no more 0, but it's still a very small signal. So you can use just a linear equation where it was mu n COX W over L, V effective times VDS, right? And that's your 1 over R. And so it's a simple, algebra after that. So basically, it's asked you to find out that I think the bandwidth required is 250 megahertz, right? So basically, they want this. So this is your RDS, and this is your C, let's say that's your load, CL. So you know CL, your bandwidth required, so you can calculate the RDS, I think, which if you calculate will turn out to be around 636 ohms, right? So how do you get 636 ohms? Well, you know mu n COX, you know V effective, you can find out W over L from that, right? And that W over L, I think if you calculate using all that, is 3.36. Well, I haven't written W over L, but I've chosen the minimum length here. Okay, so whatever that W over L is, I just quickly calculate 0.3.36 divided by 0.35. That's 9.6. So W over L is 9.6. Okay, so obviously an obvious question you might ask is, why did I choose this L? You can choose any L you want, but it's just a waste of your area, one thing. But if you see the second part of the question, it's asked you CGS, right? And CGS is COX times W times L. Now, you want this area to be the minimum because something is going to drive this, right? Like you could have a clock driver or something is going to be driving this. So you want this capacitor to be the minimum, which means that you choose your L to be minimum, and then whatever W is required for that to get your 636 ohm resistor. For example, if I increase this to, let's say 0.7 micrometer, then this will increase to 3.36 times 2, which is roughly about 7 micrometer. That'll still give you the same resistance, 636 resistance, but this CGS will go 4x now, right? So if you have a clock driver, for example, driving this or whatever it is, then your power is going to go up by square of that, which is like 16x. So in situations like this, you will choose the minimum length, right? But when we're doing current mirrors, the ones we have given, we'll see that we actually don't want to use minimum length. There, our lengths, we want it higher. Okay, I think the rest of the problems, I probably don't have to go through it because it's pretty straightforward, just algebra. The first one, I think, okay, the first one I just want to quickly mention. I think in the first problem, someone, I think just few of you attempted it, and it's a, so again, some small signal VI was given and you were required to find out the bandwidth. So this R was given to be 43 kilo ohms. So this is a reverse bias, by the way. So you use the reverse bias equation, right? Some of you used actually the forward bias. You can't use a forward bias here because that'll draw a lot of current. You'll hardly have any gain here. So the only way you can have some sort of a filter here is if you have it reverse bias, because this leakage current is going to be really small and just looks like a capacitor actually. So this is that Cj naught times that whole nonlinear equation you have to use. So again, it's just straightforward algebra after that. So I'm not going to go through that. I think all other problems are pretty much similar. Okay, I think I just want to quickly cover two more things. These are very important ones when you start designing. So I think, in your the chapter I'd given you, it was The table 1.5, for example, gives you all the parameters like, lambda by L, mu n cox, and so on. Now, when you get when we get our PDK, which is our process design kit for the process we're going to design with, usually you will not get this table. You're actually going to create this table because the model which will be given to you is very complex. There are like hundreds and hundreds of parameters in it, right? So usually what you do is you do some few extraction, very rough extractions. And so that's why I wanted to emphasize this one. For example, the VT extraction. Um, if you just draw, so if you take a transistor and you plot the ID over here, ID versus VGS here, we show that it was a nonlinear equation, right? But if you actually just kind of extrapolate this point over here roughly gives you a threshold voltage VTN, right? So you can take a transistor, bias it, and sweep the current, and that'll give you a VTN. And then use this VTN for your hand calculations. It's not going to give you a close answer, like the most accurate answer, but it will guide you to pretty much 90 to 95% close to whatever you're trying to achieve, and then you can simulate after that, okay? So that'll give you VT. And you can do the same thing. So what you do is now you find the slope of this every point. Slope as a function of VGS, right? So every point you find this slope. So this is GM, right? And if you remember, that was this slope here, which was DID versus dVGS for every point here. And then if you plot that over here, that's sort of the curve you'll get, right? Now, this slope is nothing but mu n cox W over L, right? Mu n cox W over L. Because in your ID equation, you had mu n cox W over L times the GM part of it, which means that if you take the slope of that, then if you take the slope at every point, then the constant will be actually this factor. And you know this one because that's what you use. So if you know W over L, this slope is mu n cox divided by that W over L is what, you take the slope and divide it over W over L, and that'll give you mu on cox, okay? Just, if you're getting a little confused right now, just write the equation. You'll see how the linear slope comes into picture. And the same thing with estimating lambda. So this is your ID versus sorry. So that's your reason for RDS, right? Which is DIDS over DVDS. Sorry, 1 over RDS is DID over DVDS. Again, now if you take the slope of this for every VDS and plot it here, you can see that the slope is going to change drastically here and should be pretty constant in this area, right? Like as I said before, it's changing slowly. So that's your GDS. And if you plot this GDS over ID, this factor over here, GDS over ID, during that flat region, that gives you lambda. For example, here it's roughly about 0.45 voltage inverse. And this is as a function of VDS. So this is the way you would, sort of extract parameters from it, and that's how you create your table 1.5, because like as I said, once we get your PDK, you're not going to get that table. You're pretty much going to create it. So you just extract few of the most important parameters, and then that way you'll start designing it. So every time you have a problem in your circuit, you can quickly hand calculate and find out, okay, I need to increase the current or decrease the current or this much, for a given value of current, I need this much GM, or I cannot do with this GM. Those are the things you can quickly calculate and then use the simulator after that to fine tune it. Okay. Okay, I think I'll just stop the recording here and then we can